For years, if you wanted to achieve state-of-the-art language generation, you really only had like one viable architectural option.
Yeah, left to right autoregressive transformers.
Exactly. I mean, it has essentially been treated as a religion in the AI community. The assumption was always, language is sequential, so the model must be sequential.
Right, it's just accepted as fact.
But today, we're looking at a paper that practically proves that religion might be wrong. Welcome to AI Paper Slop, the YouTube series where we summarize the bleeding edge of AI and tech papers so you don't have to wade through the PDFs yourself.
And this one is definitely worth your time.
Oh, absolutely. We are jumping straight into a fascinating paper titled Improved Large Language Diffusion Models. It introduces a model named iLLaDA, and here's the core insight you need to know right up front.
Let's hear it.
So researchers at Renmin University and ByteDance, they have trained an 8 billion parameter masked diffusion language model entirely from scratch.
Entirely from scratch.
Yeah. And they scaled pre-training up to a massive 12 trillion tokens with fully bidirectional attention. And the result? iLLaDA is highly competitive with top-tier autoregressive models like Qwen 2.57b.
Which is honestly wild to think about.
Right. We are talking about major architectural shifts here. They adapted grouped query attention natively for diffusion. They used variable length block generation for inference. And this is the craziest part. They found that diffusion LLMs don't suffer from catastrophic SFT collapse even after, 12 epochs of data reuse.
Yeah, which is the kind of claim that makes anyone working in the autoregressive space do a double take.
Yeah.
I mean, normally, you run supervised fine-tuning for 2, maybe 3 epochs max.
Right, before the model just memorizes the training set.
Exactly. It loses all generalizability. So the fact that a masked diffusion model can absorb that level of repetition, it's a massive shift in how we need to think about data scaling laws and optimization.
So let's pull this apart. We know the headline, right? A diffusion LLM is directly threatening the autoregressive monopoly. But if I'm an ML engineer looking to replicate this or build on it, I want to know the plumbing.
Sure. Let's dig into the base architecture.
So it's a dense transformer backbone, and they are using standard components we all know, RMS norms, SWGLU activations, ropey embeddings, and they stripped out all the attention and MLP biases, standard optimizations.
Very standard, yeah.
But then they make this major surgical tweak from the original LLaDA architecture. They swapped out standard multi-head attention for grouped query attention, or GQA.
Yes, and that is a pivotal decision for making this model actually usable in production.
But wait, let me hypothesize here, because this is where my intuition clashes with diffusion. We use GQA in modern autoregressive models to, shrink the KV cache memory footprint during generation.
Right, you have fewer key and value heads.
Exactly. So you store less in memory as you generate token by token. But inference in diffusion is fundamentally different. The entire sequence updates simultaneously during the denoising steps.
It does.
You aren't just appending one token to a frozen past context. So, what are you even caching? Is the switch to GQA here purely to match the parameter budget of autoregressive models? Or is there a way to actually cache memory in a bidirectional setup?
It's actually the latter. And it leans heavily into recent breakthroughs in how we handle diffusion inference. Because you're completely right. Traditionally, caching in diffusion was just a total nightmare.
Right, because everything updates constantly.
Exactly. The sequence representations update at every single time step. But the inference method used here relies on locking in certain tokens.
Oh, locking them in.
Yeah. If the model is highly confident about a subset of predicted tokens, it permanently unmasks them. It essentially locks them in as visible context for the remaining denoising steps.
Okay, I think I see where this is going.
Right. So once a token is locked and visible, its key and value representations do not change in subsequent forward passes.
Ah, I see. So you can actually cache the K and V matrices for the locked tokens. That completely bypasses the need to recompute attention for the frozen parts of the sequence at every diffusion step.
Precisely. By implementing these new cache-style inference methods, the memory bottleneck suddenly mirrors the autoregressive bottleneck. The KV cache grows as more tokens get locked in.
So introducing GQA, where you share key and value heads across multiple query heads, that drastically reduces that memory footprint.
Exactly. It makes it feasible to actually serve an 8 billion parameter bidirectional model without immediately running out of VRAM.
That is incredibly clever. It bridges the gap between the two paradigms perfectly.
It really does.
And speaking of memory bandwidth and parameter budgets, they also utilized parameter tying. They tied the input embedding weights and the LM head prediction weights together.
Yeah, standard practice to save memory.
Right. It drops the total parameter count from about 8 billion down to 7.62 billion. But honestly, what I find much more interesting than the parameter count is how they structured the data batches during that 12 trillion token pre-training run.
Oh, the sequence length.
Yeah. They use a maximum sequence length of 192 tokens. But they don't just feed it uniform blocks. About 30% of the time, they randomly split an 800 and 192 token sequence into two shorter, totally independent segments.
Which, as an engineer, introduces a serious challenge. I mean, if you are building the data loader for this and you have irregular sequence lengths inside the exact same batch, the naive approach is to just pad the shorter sequences with zeros up to the max length.
But at a 12 trillion token scale, padding tokens mean you are doing millions of dollars of matrix multiplications on literal empty space. You're wasting massive compute. So how do they get around materializing that padding matrix?
They completely bypass standard padding by using a flash attention-based variable length attention kernel.
Okay, how does that work in practice?
So instead of a traditional dense batch, they pack these variable length examples into a single flattened 1D sequence array. Then they pass a vector of cumulative sequence lengths to the kernel.
That's often referred to as Q-sequence in the PyTorch ecosystem, right?
Exactly, Q-sequence.
Right, so the attention kernel natively knows the exact index boundaries of each actual sequence within that flattened array.
You got it.
It calculates the attention block by block, completely isolating the sequences without ever calculating attention across the boundary of a split segment.
Exactly, so it achieves 100% compute efficiency on the actual tokens. No wasted FLOPs on padding whatsoever.
That's huge.
But here's the thing. Even with perfect compute efficiency, when you train at that 12 trillion token scale, optimization dynamics get weird.
Oh, they always do.
And the authors were very transparent about this in the paper. They hit a severe pre-training loss plateau. The loss just totally flatlined.
Ugh, the dreaded plateau. Every ML engineer training a large model has stared at that flat one chart in just pure despair.
It's the worst feeling.
I've seen people try to restart from earlier checkpoints with different seeds or tweak weight decay. What did they actually do to break out of it?
They actively intervened in the learning rate schedule. So they had been using a constant learning rate after the initial warm-up phase. But when they hit the wall, they dynamically switched to a cosine decay schedule with a minimum learning rate of 5 times 10 to the negative 6.
Wait, why does that specific intervention work? Like, why does dropping the learning rate via cosine decay kick a plateauing loss back into a downward trend for a diffusion model?
So when you maintain a constant, relatively high learning rate deep into a massive training run, the model parameters can start sort of bouncing around the walls of a local minima.
The step sizes are just too big.
Right. The steps are too large to settle into the deeper, narrower valleys of the loss landscape. So by triggering the cosine decay, you systematically reduce the step size. It allows the optimizer to effectively cool down and converge into those tighter, more optimal weight configurations.
That makes total sense. It's a great reminder that scaling laws aren't just about throwing GPU hours at a static script, you know? You have to actively babysit the optimization dynamics.
You really do.
Okay, so they babysat the optimizer, they bypassed padding with flash attention, and they have this robust 12 trillion token pre-training engine running smoothly. The model is essentially a massive, highly capable autocomplete for corrupted text.
Pretty much.
But users don't write prompts with random blanks in them. Users write instructions. They expect a chatbot. So how do you force a fully bidirectional, non-autoregressive model to actually follow instructions during supervised fine-tuning? I mean, the standard left-to-right SFT format where you give it a prompt and it learns to predict the response, that just doesn't make sense here.
No, it doesn't at all. And in the early days of diffusion language models, people used a bit of a hack to get around this.
What did they do?
Well, they would concatenate the prompt in the response, but during training, they would force the prompt tokens to remain visible and only apply the noise or the masking to the response region.
So they were essentially trying to force a bidirectional model to act like an autoregressive one during fine-tuning.
Exactly. It was a compromise.
But iLLaDA throws that split masking idea right in the trash, doesn't it?
It really does. They format the SFT instance natively, so it's the prompt, the response, and a single terminal EOS token. And then they apply the exact same random masking scheme they used in pre-training across the entire sequence.
Oh, wow. That means the prompt, the response, and the EOS token can all be masked simultaneously.
Right, which is mathematically beautiful because it maintains the core bidirectional objective. The model isn't just learning a conditional probability, how to generate a response given a fixed prompt.
It's learning the whole thing.
Exactly. It is learning the joint distribution of the entire instruction interaction. It's learning how the response constrains the prompt, and inversely, how the prompt constrains the response.
And this leads right into what is arguably the most disruptive finding in this entire deep dive into the paper. If you are an ML engineer listening to this, and you've ever fine-tuned an autoregressive model like Llama 3 or Mistral, you know the golden rule. Do not overtrain on your SFT data.
Absolutely do not.
If you let an SFT run go for 12 epochs on the exact same instruction data, your model is completely fried. It memorizes the data, catastrophic forgetting kicks in, and it's basically useless for anything outside that specific distribution. But iLLaDA took a 25 billion token instruction corpus and fine-tuned for a staggering 12 epochs.
Yeah, and not only did it not collapse, it actively improved.
That's insane.
Right. If you look at their ablation studies, the performance on reasoning-heavy benchmarks like GSM-8K for math and MMU Pro for general knowledge, it just kept climbing continuously as the SFT epochs increased.
So how does diffusion get a free pass on the golden rule of overfitting? What is the actual mechanism preventing catastrophic memorization here?
The free pass is natively built into the continuous masking mechanism itself.
Okay, unpack that for me.
Think about an autoregressive model. The learning signal for a specific sequence is deterministic. Every time it sees token A, it is penalized if it doesn't predict token B. So by epoch 3, the model has seen that exact static path multiple times and just memorizes the sequence weights.
Right, it just learns the rote path.
But in a masked diffusion model, you are sampling a random masking ratio between 0 and 1 at every single training step.
Oh. So one epoch, a specific instruction example might have, say, 20% of its tokens masked. And then the very next epoch, that exact same prompt and response, might have 85% of its tokens masked and in completely different positions.
Exactly. This acts as infinite native data augmentation. Every single time the model sees the same high-quality SFT example across those 12 epochs, it is seeing a completely unique pattern of corrupted context.
Oh, that makes so much sense.
Right. The model is forced to reconstruct the missing pieces from drastically different visible hints each time. It literally can't memorize a left-to-right path. It has to build a much deeper, more robust internal representation of the logic connecting the prompt and the response.
So it extracts magnitudes more signal from repeated exposure to the exact same data.
Yes, exactly.
That is wild. It essentially turns data scarcity into an advantage, as long as you have high-quality SFT examples. Okay, so we have a fully trained, fine-tuned model that thrives on bidirectional context and heavy data reuse. Let's talk about inference. When you finally hit enter on a prompt, how does it actually sample and generate text? We touched on this briefly with the GQA KV cache, but let's dive into the actual algorithm. They use what's called variable length block generation.
Right. Instead of predicting one token at a time, you have to think about inference as iterative refinement.
Let me try to visualize this for you. Think of it like solving a really complex Sudoku puzzle.
I like this analogy.
Thanks. So you don't solve Sudoku by starting at the top last square and moving strictly left to right, row by row. That's how an autoregressive model works. With Sudoku, you scan the whole board. You fill in the obvious numbers first, the ones you have the highest mathematical confidence in based on the visible board.
Right. The easy wins.
Exactly. And those new numbers immediately constrain the rest of the board. Then you revisit the blank spots, the ones you weren't sure about on the first pass. And now, because of the new context you just filled in, they are easier to solve. You just iterate until the puzzle is full.
That analogy maps perfectly to the block generation algorithm. At inference, they take the user's prompt and append a block of mask tokens. The model runs a forward pass and predicts a probability distribution for every single mask position simultaneously.
But it doesn't just accept the argmax for all of them, right?
No, it doesn't. It ranks its predictions by confidence. It takes the highest confidence predictions, unmasks them, and permanently locks them in as visible tokens.
And the ones that had low confidence in?
It simply remasks them. Then it runs the next denoising step. So the previously locked tokens now act as high-quality bidirectional context, making the remaining masked tokens easier to predict. It just repeats this refinement loop until all tokens in the block are locked, or an EOS token naturally halts the generation.
It's just a completely different paradigm of text generation. But, open-ended generation is really only half of the benchmark battle. Evaluating these models on multiple choice benchmarks like HelloSwag, POQA, or ARC Challenge requires a completely different approach.
It does.
Because in standard autoregressive evaluation, you just calculate the log likelihood of each possible candidate answer and pick the highest score. It's clean math. But doing that for diffusion is notoriously noisy.
Very noisy. The mathematical proxy for log likelihood in a diffusion model is the evidence lower bound, or the negative log likelihood upper bound. The problem is that calculating this bound requires taking an expectation over all possible continuous noise levels, or masking ratios. When you are trying to compare two very similar short candidate sequences in a multiple choice test, integrating over all those noise levels introduces a lot of variance.
So the theoretical average doesn't always reflect the model's actual generative capability.
Exactly.
So how do you evaluate multiple choice fairly? The authors introduce a deterministic confidence-based scoring rule, if I'm understanding this right. They essentially force the model to take a multiple choice test the exact same way it generates text.
Exactly. They basically strip away the noise of the expectation. So let's say you are testing candidate answer A. They start with the whole candidate answer masked. They ask the model, out of all these masked positions, which ground truth token of candidate A are you most confident about?
Okay.
The model points to 1. They reveal that specific ground truth token, lock it in, and record the log probability the model assigned to it.
And then they ask again. Given this newly revealed token, what is your next highest confidence token for the remaining masks? They reveal it, log the probability, and repeat until the whole candidate is unmasked. Then they just sum up those specific highest confidence log probabilities.
Yes. By forcing the model to iteratively lock in its highest conviction prediction step by step, you are evaluating the deterministic reasoning path the model actually takes during inference.
That's super smart.
It aligns the evaluation metric perfectly with the generation mechanics, and the results really validate the theory. This confidence scoring trick improved HelloSwag scores by 2.3 points and PIQA by 1.3 points over the standard likelihood method.
Okay, so all the theory in architectural hacking is brilliant. But for the researchers and engineers tuning in, the benchmark table is the final judge. How does iLLaDA actually stack up against the reigning 8B champions?
The results for the base model are genuinely disruptive. iLLaDA completely outclasses previous diffusion models like the original LLaDA, but the real comparison is against Qwen 2.57b base, which is arguably the most highly optimized autoregressive model in that size class.
And iLLaDA holds its own. Like, on average, iLLaDA base is actually slightly stronger than Qwen 2.57b base. On MMLU, which is the gold standard for general knowledge, iLLaDA scores 74.8 compared to Qwen's 71.9.
That's a solid beat.
Yeah, and on the Big Bench Hard, or BBH, which evaluates complex reasoning, iLLaDA hits 71.3, while Qwen hits 63.9.
Those numbers are a massive signal to the field. I mean, it definitively proves that left-to-right causal attention is not a prerequisite for building strong base language representations. The bidirectional objective produces a fundamentally competitive and, in some areas, superior foundational understanding of language and logic.
But we do have to look at the whole picture. When we move from the base models to the instruct models, the ones that have undergone post-training, there is a noticeable gap. iLLaDA Instruct improves massively, hitting 65.9 on Human Evil for coding and 89.0 on GSM-8K for math, but it still lags behind Qwen 2.57b Instruct.
Right, because Qwen hits 84.8 on Human Evil and 91.6 on GSM-8K.
So why does the diffusion model fall behind when the tasks get strictly logical?
To understand the gap, we have to look at a really fascinating bug the researchers encountered during the supervised fine-tuning phase. On particularly complex reasoning problems, iLLaDA would frequently get stuck in repetitive reasoning loops.
Oh, really?
Yeah, it would output phrases like, wait, let me check again, or let me rethink this, and it would just spin its wheels infinitely, never actually committing to a final answer.
Wait, why does bidirectional attention cause self-doubt? If I had to guess, I'd say it has to do with the training data. The SFT corpus is likely packed with structured chain-of-thought traces from other reasoning models.
Yep, exactly.
And those traces frequently include self-correction phrases. So because iLLaDA fills in blocks based on surrounding context, if the context is highly complex, the model essentially predicts that the most probable next step is to doubt its own work.
That is exactly what happens. It's basically a victim of its own bidirectional awareness. It sees a complex problem, sees its own intermediate steps, and the joint probability of generating a self-correction phrase just spikes.
So how did they fix it?
To fix it, the researchers implemented a dynamic intervention during inference. As the generation sequence gets longer, they dynamically increase the probability of the think token. They literally have to artificially force the model to stop doubting itself, terminate the reasoning trace, and output a final answer.
Wow, it's a very clever hack. But it points directly to the reason for the performance gap in math and code, doesn't it? Quen 2.5 relies heavily on reinforcement learning like RLHF or similar alignment techniques after the SFT phase. iLLaDA is purely an SFT model. It has no RL alignment yet.
And that is the missing piece of the puzzle. The gap isn't a failure of the diffusion architecture. It is just a missing step in the post-training pipeline. Reinforcement learning is specifically what teaches autoregressive models to reliably navigate complex, multi-step reasoning chains without getting stuck in loops.
Right. They learn which reasoning paths yield high rewards and which ones are dead ends.
Exactly. So once post-training methods like variance-reduced preference optimization or diffuse GRPO are adapted and applied to iLLaDA, we should fully expect that math and coding gap to close.
This has been an incredible breakdown. We have traced iLLaDA from its 12 trillion token bidirectional pre-training, unpacking how flash attention and GQA keep the memory footprint competitive. We've seen how random masking acts as native data augmentation, allowing an unheard of 12 epochs of SFT without collapse.
Yeah, that was huge.
And we've explored the Sudoku-style block inference and confidence scoring that allows it to go toe-to-toe with the best autoregressive models in the world.
The overarching takeaway for anyone listening is clear, really. The tooling is catching up, the caching mechanisms are here, the scaling laws are maturing. Diffusion is a highly viable competitive architecture for text generation at scale.
It really is.
Relying entirely on autoregressive factorization was starting to feel like the industry was stuck in a local minimum, and this paper breaks us out of it.
I completely agree. And that brings me to a final thought I want to leave you with. We just talked about how iLLaDA operates bidirectionally, filling in high-confidence tokens, remasking low-confidence ones, dynamically checking its own context, and we noted that it hasn't had reinforcement learning applied to it yet. So what happens when we finally apply modern RL to this specific mechanism? Unlike a left-to-right model that is forever tracked by the past tokens it just generated, a diffusion model has the inherent architectural ability to look ahead, doubt itself, and dynamically revise its own internal thoughts before locking in a final answer. Could this non-autoregressive nature eventually make diffusion models fundamentally superior to autoregressive models at complex multi-step logical reasoning? Think about the implications of that as you read the next wave of ML papers. Thanks for tuning into AI Paper Slop, and we'll catch you on the next one.